Okay, so we finished with the disjoint thing yesterday. So, are traveling to Mexico and Canada independent events? So, to test that, we're going to see if the probability of Canada is equal to the probability of Canada given Mexico. So, the probability of Canada was given to us in the problem to be 0.18. And the probability of Canada given Mexico, we found in part D, was 0.44. Those are not equal. Come back. Those are not equal, so not independent. All right. In its monthly report, a local animal shelter states that currently has 24 dogs and 18 cats available for adoption. 8 of the dogs and 6 of the cats are male. What is the probability of randomly selecting a male pet given that it is a cat? So, I would suggest making a table to start with. Just because it's kind of confusing how that stuff is laid out. So I would say we have male and female, and then we have dog and cat. So we're told that 8 of the dogs are male and 6 cats are male, so I can fill that in. And then we just have to subtract that value from the total number to get the female. So 24 dogs minus 8 dogs is 16 dogs that are female, and then 18 cats minus 6 cats is 12 cats that are female. So now, what is the probability of randomly selecting a male pet given that it is a cat? So total dogs, we have, what's 24 plus 18? 42? 42 total animals. And then overall we have, just to give us the total, so we have 14 males, 28 females, and then that way we can actually answer all of our questions. All right, so selecting a male pet given that it is a cat, so that is the probability of male given that it's a cat. So we have the intersection of the two, so the probability of male intersected with cat divided by the probability that it's a cat. It's always the second thing. So male and cat, there's 6 of those out of the total number of cats is 18. So that would be 0.33. So then the next one, the probability of randomly selecting a cat given that it's female. So the probability of cat given that it's a female, it's equal to the probability of the intersection of both, so cat and female, divided by the probability of female. So female cat, we have 12 out of the total number of females, 28. And that ends up being 0.43. All right, what is the probability of randomly selecting a female pet given that it's a dog? How did I set that one up? So, female dog, 16, or wait, yeah, is 16. Probability of dog is 24. And that ends up being 0.67. Or 0.66, repeating, whatever. So, are the species and sex of the animals independent? There's a few different options, so you can pick whichever one you want to do.
Take the probability of a male dog. Probability.
Well, so we just, or are you saying male given that it's a dog?
Yeah.
Okay.
And then you would take the probability of the female dog.
It's got to be one of these two things.
Just a dog.
Okay, so if we're going to do dog, we have to flip this.
Okay.
So if you want to do the probability of a dog, then I need to do dog given male. Now, I will tell you, my only hesitation with doing this is that you have to do more math because you didn't choose to use something that you already know, which is fine. We can do it. I'm going to do it, but I'm just saying I usually try to pick something that I've already found. So, but we can still do this. So this is the probability of dog intersected with male divided by the probability of male should be equal to the probability of dog. So the intersection is 8 divided by 14 is equal to the probability of dog is wait. Okay, it's 24 out of 42, so whatever that ends up being. So 8 divided by 14 is 0.57. And 24 divided by 42 is 0.57. So since they're the same, it is independent. So totally fine to do it that way. It just makes more work. So if you want to get out the easy way, just use one that's already given to you. The next example is kind of like that. Do you feel like you need to see that one, or we can? I don't care.
What's that example?
Yeah, it's basically like what we just did. I'm okay with doing it if you want to. If you're like, no, I got it.
Yeah, let's do it.
Okay. All right, so the question, do you smoke, was asked of a random sample of 100 people. Results are shown in the table below. Suppose we select one of the people at random. So we have male or female and then yes or no. So what is the probability that a person smokes? So we have the probability, or like that they said yes that they smoke out of the total number of people. So that's 31 out of, 100, which is 0.31. So then how do I find the probability of smokes given that they're male?
So you would do the probability of smoking a man equals over probability.
Yep. So smokes and is male is going to be the yes for male, so that's 19 out of the total number of males, just 60. And that is 0.32. So then, is smoking and gender independent? Well, so we have to show it.
Oh, it's not good.
So we would want to show, since we used smoking and male here, and we know what that, or like, we know what this smokes, given that they're a male, came out to be 0.32. We're going to want to use that. So the probability that they smoke, given that they're a male, would be equal to, it's the probability that a person smokes. So it was 0.32. Probability that a person smokes was 0.31. Those are not equal, though they're similar. So it is not independent. Oh man. Okay. There's not a ton of room. Does your paper look like this, or does your paper have another page to it? Like, does it look like this, or does it look like the bottom of my screen? Okay. There's not enough room to write. Okay. It's annoying. Okay, we might have to write small. It's not like that big, but anyways. All right, so, because we're going to be drawing the diagram. A manufacturing firm orders chips from 3 different companies, 10% from company A, 20% from company B, and 70% from company C. Some of the chips that are ordered are defective. 4% of chips from company A are defective, 2% from B are defective, and 0.5% from C are defective. If a computer chip is selected at random and found to be defective, what is the probability that it came from company B? So I'm going to set up basically a branch here for each company. So A, B, and C. So this is all given information. So so this is going to be where the chips came from, and then we're going to do if they were defective or if they were okay. So 10% are from A, so that's 0.10. 20% from B, so 0.20. And 70%, so 0.70 from C. Then our next branch is if they are defective or if they were okay for each one. So, and just because I don't have a lot of space, I'm just going to write them right at the end. But for the defective ones for A, that was 4%, so 0.04, meaning that the rest of them are okay, so that would be 96% or 0.96. B had 2% effective, so 0.02, meaning that 0.98 were okay. And then C would be defective 0.005 and okay would be 0.995. So we're looking for if a computer chip is selected at random and found to be defective, what is the probability that it came from company B? So that's saying we want the probability of B given that it was defective. So probability of the intersection of the two, divided by the probability that it was defective. So the intersection of the two, we're just multiplying the numbers in the row. So 0.2 times 0.02. Now the probability of defective, we have to do all the defective ones. So we have to multiply each company percentage of how many chips they did times the ones that were defective. So this would be over 0.1 times 0.04 plus 0.2 times 0.02 plus 0.7 times 0.005. So this was A, B, and C being defective. And when you plug all that in, that ends up giving you 0.348. Okay. Alright, we're gonna have to make a diagram for this one too, so I'm trying to figure out. I might just like start it over here or something so I have room. Suppose that 23% of adults smoke cigarettes. It's known that 57% of smokers and 13% of non-smokers develop a certain lung condition by age 60. Explain how these statistics indicate that lung condition and smoking are not independent. So we're going to set up the diagram, and then in the box we'll actually do if they're independent, or to show if it's independent or not. So we're going to have just two branches off this time for smoking and non-smoking. I'm just going to do S and NS for not smoker or non-smoking. And then I'll have to put the numbers in a second. Oh. So the only reason it's not is because there's multiple conditions that are occurring. So if it was just like smoker and non-smoker or something, like we would do the Venn diagram, but since we're caring about lung condition as well, that's why we're doing it this way. It's like two things that we care about. So then this is going to be if they have a lung condition or no lung condition. So 23% of adults smoke, so that's going to be 0.23. So then non-smokers are everyone else, so that would be 0.77. Then lung condition, so 57% of smokers have a lung condition, so that's going to be 0.57, and the rest do not, so 0.43. Then non-smokers, 13%, so 0.13, and then the rest would be 0.87. So then it says to explain how these statistics indicate that lung condition and smoking are not independent. So I would do the probability of a smoker should be equal to the probability of a smoker given that they have a lung condition if they're independent.
So it'd be like probably the smoker. Be 0.23
Yep.
equals 0.23 equals 0.23 over 0.57.
Well, so this On top would be the intersection of it. So, like, it would be the intersection of smoking and lung condition. So we would multiply those numbers together. Because wait a second. Yeah. Hold on. Brief pause. Make sure I have the right thing down here. So this would be, I'm going to draw it off to the side and then I'll write what it's equal to. So the probability of smoking intersected with lung condition divided by the probability of the lung condition. So we would do the same thing like we did here. So the intersection, we would multiply smoking times lung condition. So it would be 0.23 times 0.57 divided by lung condition. So that'd be 0.23 times 0.57 plus non-smoker and lung condition 0.77 times 0.13. So 0.23 times 0.57 is 0.1311 divided by plus, let's see, 0.77 times 0.13 over 0.2312. 0.1311 divided by that is 0.57. So that one happened to actually be literally the same thing. So that's 0.57 then. Those are not equal, so it is not independent. And basically another thing that you could tell is you would expect in this scenario that the same percentage of people would have a lung condition, smoking and non-smoking, if it was independent. So, all right. What is the probability that a randomly selected 60-year-old has this lung condition? So, has a lung condition would just be the bottom of this. It would have been the probability of a lung condition. So it would have been 0.23 times 0.57 plus 0.77 times 0.13. So that is 0.23 basically. What is the probability that someone with the lung condition was a smoker? Okay, so this one's actually one that's written backwards. So this is the probability of a smoker given that they had a lung condition. It's just written backwards the way that they wrote it. So you have to kind of, these are sometimes ones you have to read a couple times to make sure you understand it. So this is the second part of this. Technically that was already worked. So I'm just gonna I guess it would have been better if we did B and C and then tried to do A, but it's fine. Questions?